Okay, so for all you AI brainiacs out there, buckle up, because we're diving into something pretty cool today. We're cracking open this paper. The first few tokens are all you need for fine-tuning reasoning models. And just to kick things off, for those who want the TLJD, the big takeaway here is you can basically supercharge a large language model's reasoning abilities just by focusing on the first few steps they take, the first few tokens they generate when they're trying to solve a problem.
It's a bit like judging a book by its cover, but in this case, it seems like the opening lines actually do reveal a lot about where the story is going.
Exactly. It's all about this method they've come up with called UPFT, Unsupervised Prefix Fine-Tuning. And it's pretty remarkable. They're showing it can match the performance of the usual heavy-duty supervised fine-tuning, but get this, it uses way less training time. We're talking cutting it down by like 75%. And the sampling costs, forget about it, almost 99% less.
That's a huge efficiency boost. I mean, anyone who's worked with these models knows how resource-intensive those traditional methods can be.
Totally. It's like we're always throwing more compute at the problem. So let's unpack this UPFT thing, shall we? We'll get into the nitty-gritty of how it operates, why those first few tokens are so darn important, and what this could mean for building, smarter, more efficient reasoning models in the future. And of course, we're basing all this on this paper, a really well-done paper by Zhao et al.
The foundation of this UPFT method is something they call Prefix Self-Consistency, which is a pretty intriguing observation. Can you kind of break down what that means, what they've discovered there?
Yeah, so picture this. They noticed that when a large language model tries to reason its way through the same question multiple times, even if it doesn't always get the final answer right, it might mess up somewhere along the way, the very beginning of its thought process tends to be incredibly consistent. It's like there's this shared initial reasoning phase, and that's what they're calling the prefix.
So even when the model solutions diverge later on, it seems to consistently start from the same set of premises or assumptions. It's sort of like a detective always starting at the crime scene, no matter what theories they develop later.
Yeah, great analogy.
Yeah.
And they've got some pretty solid evidence to back this up. In figure 2A of the paper, they ran this experiment where they had these LLMs, Llama 3.18b instruct and Quinn 2.5 math 7b instruct. That one's a bit of a mouthful, but it's specifically good at math. Tackle a bunch of questions from the PRM dataset. And they did it like 1,000 times, generating all these different reasoning paths. And what popped out was this remarkable overlap in the initial sequences of tokens, especially the very early ones.
So even across 1,000 attempts, those first few steps were remarkably similar, suggesting a kind of inherent structure or consistency in how the models approach these problems. And I bet that Quinn math, being designed for math, was even more consistent, right?
You bet. It makes sense, doesn't it? When you're dealing with something as structured as math, there might be fewer valid starting points, so to speak. Then they dug deeper in figure 2b, looking at where those inconsistencies and ultimately the errors start to creep in.
This is where the rollout success rate comes into play, right? It's like taking a snapshot of the reasoning at a certain point and then seeing if the model, left to its own devices, can correctly finish the job from there.
Exactly. So they found that if you look at the reasoning paths that ultimately led to a wrong answer, the chances of rolling out successfully from those later tokens, like halfway through or towards the end, plummeted. It's like once the model takes a wrong turn, it gets lost in the woods.
But the key insight, the one that fuels UPFT, is what they observed about those initial tokens. What was the trend there?
It's pretty mind-blowing, actually. For those very first few tokens, maybe up to the first 16 or so, the rollout success rate was pretty much the same, whether the overall reasoning path ended up being right or wrong. The paper even says these early tokens are basically statistically indistinguishable in terms of whether they'll lead to the right answer.
Wow. So it's like the model has a knack for starting off on the right foot, even if it stumbles later on. It seems like there's something special about those initial steps.
Totally. So now we're starting to see why this UPFT method might be onto something. If we can just train the model to consistently generate those promising early prefixes, the chances of getting the whole answer right go way up. But before we get to that, let's touch on the old way of doing things. Rejection sampling fine-tuning, or RFT. How does that work, and what are the downsides?
RFT is kind of like a brute force approach. You generate a ton of different reasoning attempts for a single question, and then see which ones actually give the right answer. Then you only keep the ones that were successful and use those to fine-tune the model.
It's like throwing spaghetti at the wall and seeing what sticks. But you can imagine it gets pretty computationally expensive and time-consuming to generate all those paths, most of which end up being useless.
Right, and you absolutely need labeled data, the correct answers, to even do it. So Enter UPFT, which takes a much more targeted and efficient approach. How does it leverage this prefix self-consistency to get around those issues?
The beauty of UPFT is its simplicity, really. Instead of training on entire reasoning sequences, which can be long and convoluted, it focuses solely on those short initial prefixes. And they found that even something as short as 8 tokens could make a big difference.
And the fact that it's unsupervised is key here, right? We're not relying on labeled data for this prefix fine-tuning, which makes it way more scalable and data efficient.
Absolutely. It's like saying, hey model, we've noticed you tend to start off pretty well. Let's just make those starting moves even stronger. And because you're only dealing with these short snippets, the computational savings are enormous.
But then, how do you ensure the model can still generate a full reasoning path and follow instructions that require longer outputs? If you're only training on these short prefixes, wouldn't it lose the ability to generate complete responses?
That's where they introduce this clever structure tuning trick. They do a small amount, they call it P% of full-length fine-tuning. But here's the catch. They don't even bother checking if the answer is correct.
So it's not about getting the right answer during structure tuning, it's just about reminding the model how to generate a complete, coherent response that follows the general structure of the task.
Exactly. And they even use a specific task template for the prefix tuning. Something like, here's the question. Now just give me the first step towards solving it. You don't need to solve the whole thing, just lay the groundwork.
I'm looking at figure 3 in the paper, and that's pretty much it. It explicitly tells the model to focus on that initial stage. It's like a guided exercise for those first crucial steps.
Yep. Very clever. And then they bring it all together, the prefix tuning and the unsupervised full-length tuning into one unified training objective. It's all laid out mathematically in equation 8.
Now, to understand why this focus on prefixes works so well, they actually analyze rejection sampling fine-tuning, the old method, from a Bayesian perspective. Can you walk us through that? I think it's a pretty illuminating way to look at it.
Sure. So they break down the probability of getting a correct answer into 2 parts, coverage and accuracy. Coverage is basically how well the model explores different possible ways to solve the problem. Does it consider a variety of approaches, or does it get stuck in a rut?
And accuracy is, given a specific reasoning path, how likely is it to actually lead to the correct answer? So it's about both exploring options and choosing good ones.
Right, and what they suggest is that RFT, by only focusing on completely correct paths, might be accidentally limiting the coverage part. It's so focused on getting the right answer that it might miss out on learning from some valuable, albeit partially incorrect, reasoning strategies.
It's like only studying the perfect students and ignoring everyone who makes a mistake, even if they have brilliant ideas along the way. You might miss out on some unconventional but effective approaches.
Exactly. So by zeroing in on just the prefixes, they propose these ideas of prefix coverage, how well the model explores different starting points and prefix accuracy, how likely those starting points are to lead to the right answer. They argue there's a sweet spot, a prefix length, that balances exploration with accuracy.
It's about finding those initial good moves without getting bogged down in the later steps, which might be more error-prone. Makes sense. Now let's talk about the experiments. What models did they use to test this out?
They picked a few different models, each with its own strengths. They used Llama 3.18b Instruct, which is a good all-rounder, Quinn 2.5 Math 7 Do Instruct, our math whiz, and then DeepSeek R1 distilled Quinn 7b, which is known for handling longer reasoning chains really well.
And they used a mix of established reasoning data sets and a new one designed to be particularly tough. What was the thinking behind that?
They used the standard ones, PRM, OMI2, and Limo. But then they added this new one called UHard, for unsupervised hard. It's basically a collection of really tricky questions scraped from all over the internet, designed to push these models to their limits.
So it's like giving them an IQ test to see how they handle the really hard stuff. Makes sense. Did they do any fine-tuning to optimize UPFT, like figure out the best prefix length?
Oh yeah, they did a bunch of ablation studies.
Yeah.
Figure 4a in the paper shows what they found when they varied the prefix length. Turns out there's no one-size-fits-all answer. The best prefix length depends on the model.
So different models have different thinking styles, so to speak. Some like to take smaller steps, while others prefer to plan further ahead.
Yeah, exactly. For example, Llama 8b did best with a pretty short prefix, just 8 tokens, while Quinn Math, our math guy, was pretty stable across a range of 8 to 32 tokens. And then DeepSeek R1, which tends to generate these long, elaborate responses, liked a much longer prefix, around 128 tokens.
And what about that structure tuning ratio, the amount of full-length unsupervised training they mixed in? Did they find a sweet spot there?
Yeah, they tested that out too, and the results are in Figure 4b. Turns out, a little bit of full-length training helps around 10% generally, although for the smaller Llama dataset, they found 30% was better.
So it's like a balancing act. You want to focus on those prefixes, but you don't want the model to completely forget how to generate complete responses.
Precisely. Okay, now for the big reveal, how did UPFT actually perform? Let's start with the unsupervised scenario, where they just had the models generate one response per question without any filtering.
Drum roll, please.
Table 2 has all the juicy details, and the short story is UPFT consistently beat the pants off the standard supervised fine-tuning methods across the board.
So even without any labeled data for the prefix tuning, it was significantly better. That's pretty impressive.
Yeah, for example, on that really hard UHARD dataset, Quinn Math got an accuracy of 54.5% with UPFT compared to just 51.3% with the regular supervised method. DeepSeek R1 did even better, jumping from 56.4% to 61.6%.
And I bet it did even better on those really challenging benchmarks like AME 2024 and GPQA. Those are tough nuts to crack.
You know what? UPFT seems to really shine when things get complex. And on top of that, the data efficiency gains were insane. They managed to reduce the total training sequence length by anywhere from 82.6% to, get this, 94.7%.
That's a crazy amount of data saved. No wonder the training time and memory requirements were so much lower.
Yeah, it's a game changer, really. So they also tested a supervised scenario, just to be thorough, where they used labeled data to select correct responses, like the old RFT method.
And guess what? It was either on par or even better than the established methods like RFT and V-star, while still using way fewer tokens. So even when you have labeled data, UPFT seems to be a more efficient way to achieve good results. It really zeroes in on what matters.
Yeah, for instance, Quinn Math matched RFT's accuracy, but used only 1.2% of the tokens. DeepSeek R1 even surpassed RFT with fewer tokens. And they even showed that combining UPFT with some simple answer verification techniques could boost the accuracy even further.
So it's like getting the best of both worlds, the efficiency of unsupervised learning with the added accuracy boost from supervision when it's available. Very clever.
Right. And to really hammer home this whole prefix self-consistency thing, they included a really neat case study. Figure 5 shows this example where they had Quinn Math try a math problem 16 times, generating 16 different responses.
And I'm guessing there was a ton of overlap in the initial parts of those responses, even if they went off in different directions later on.
You got it. They had the same first 32 words in many cases, even though the later steps and the final answers weren't always the same. It's like they all started with the same understanding of the problem, even if they went about solving it in different ways.
It really underscores the point that those first few tokens are incredibly informative. They capture the essence of the reasoning process.
So let's sum up the key takeaways here, just so everyone's on the same page.
Number 1, they identified and proved this prefix self-consistency thing, which is a pretty fundamental insight into how these models reason.
Number 2, they came up with this really clever UPFT method that exploits this insight to fine-tune models efficiently without needing tons of labeled data.
And number 3, they showed that UPFT is incredibly data efficient, works across different models and data sets, and is at least as good as, if not better than, the traditional supervised methods.
Boom. So what we've learned today is that focusing on those first few tokens of a model's reasoning process is a really powerful and efficient way to boost its performance. And this UPFT method could really change the game in terms of building more capable and scalable reasoning models.
It really opens up a lot of possibilities. I mean, if we can get this much improvement from just those first few tokens, imagine what we could do with more targeted architectural changes or pre-training strategies.
Right. It makes you think about how these models learn to think and what we can do to guide that process more effectively. It's pretty exciting stuff.
It really is. And for everyone listening, if you want to dig into the technical details and see all the cool experiments they did, be sure to check out the full paper by G et al. It's well worth a read.
Absolutely. And that wraps up another deep dive. Thanks for joining us, and we'll see you next time.